Hello, class. Welcome to Math 1430, Section 4.1. And my name is Doug, making another repeat performance here. All right, so this is a cute little problem we're going to do. Find the minimum value of this function with this imposed domain. Let's say x is greater than 0. So let's do the solution. So to find the minimal value of this, what we want to do is find the derivative of this function and then set that derivative equal to 0, and that will give us the critical numbers. Remember, maximum and minimal values only occur at critical numbers. They live at critical numbers. So here is, I just rewrote the function in more friendly notation perhaps for finding the derivative. It's easier like this. That way I don't have to do the quotient rule here. Okay, so this is, notice I still call this y because this is the exact same thing as the original problem. Okay, now let's find the derivative of this function. It's two terms here, so let's go term by term. So y prime, or you could call it f prime of x, whatever you want to do.
dy dx.
Or dy dx. So I wrote y prime equals, what's the derivative of x? Just 1. And then let's use the power rule here. So take that -1 and multiply it by that coefficient 5. That gives you -5 times x to the, and then remember you bump this down 1. So what's -1 minus 1? -2. And then I can rewrite that as this. Y prime equals 1 minus 5 over x squared. So again, how do you handle negative exponents? You can put that base to the positive 2 power in the denominator. Okay, so there's the first derivative. Let's set it equal to 0. So I'm going to write 0 equals 1 minus 5 over x squared. And then if we add 5 over x squared to both sides, we get this. I kind of flipped it around the equations, but this is right. And now you can look at this as a proportion if you want and set the cross products equal to each other. That's the best way to solve for x here. When you have one fraction equal to another, recognize that as proportion, and the nice quality about proportions, their cross products are always the same. So what's x squared times 1? X squared, set it equal to the other cross product. What's 5 times 1? 5. Take square roots of both sides to solve for x, and we get x equals the square root of 5. It could be plus or minus, but remember what we said, that with the implied or imposed domain, x is greater than 0. So I can't have a negative square root of 5 also as an answer. So that looks good.
And let me interrupt. This is I'm the twin brother, so I'm Dave. And what I want to say is it's very important to find these critical numbers when you're finding maxes and mins, because that's where critical numbers occur. And besides setting the first derivative equal to 0, the other way to get a critical number is to see where is the derivative undefined. Here is the derivative. It's undefined when x is 0, because 0 squared is 0, and you can never divide by 0. So it would seem that x equals 0 is another critical number. But this imposed domain means that we cannot accept 0. To be a critical number, you must be in the domain of the function. And here the domain, they tell us, is x is greater than 0.
Okay. Well said, old chap. Okay, so now that we found our critical number, let's do the first derivative test. So we're going to do this little first derivative sign chart here. Notice I put the square root of 5. That's our critical number. Now these are test points. Pick a number less than the square root of 5. Square root of 5 is roughly something over 2. So that's why to the left of it, I wrote x equals 1. That seems like a nice, easy number to choose. What happens when you plug in x equals 1 into f prime? Make sure you plug this into the derivative function, which was right over here. So when we let x equal 1, what do we have? What's 1 minus 5 over 1, which is 5? What's 1 minus 5? -4? So that's why I wrote negative. Because we're really interested in, is it negative or positive? So that's negative. And then here's another test point. Pick something bigger than the square root of 5. How about 3? And again, plug this into the derivative function. It's kind of like this idea, f prime of, now we're doing letting x equal 3. What is that going to equal? Same idea. So what's 3 squared? 9. So what's 1 minus 5 ninths? What's 9 ninths minus 5 ninths? 4 ninths? And isn't that positive? So that's why this positive is here. I put the values over here too. Okay, so since we do get a change of sign across this critical number, it does mean we will get a maximum or minimum. Notice we did say it's going to be a minimal in the problem. By the way, there is no maximum for this function because obviously if you let x equal a huge number, it's going to be a huge number as x. So in other words, doesn't this value tend toward infinity? If you let x be a number that's tending toward infinity, so there is no maximum value. Remember, for a maximum value, you need a real number answer. And you can make it as big as you want. Okay, notice like if I let x equal 10 billion, isn't 10 billion plus 5 over 10 billion? Isn't that a very small number actually? So it's roughly 10 billion. But you can make it as big, as arbitrarily large as you want. Okay, so the minimum value, the minimum y value, let's find out what it is because we did find that critical number square root of 5. So the minimum value occurs when x equals the square root of 5. So plug in the square root of 5 for all x's in the original function to find the y coordinate. So what is the square root of 5 plus 5 over the square root of 5? Well, that's what I did here. We get y equals the square root of 5 plus 5 over the square root of 5. And let's try to simplify this. Let's rewrite that first term, square root of 5, y equals the square root of 5 plus, and with here, I just multiply top and bottom by the square root of 5. And doesn't that give me 5 times the square root of 5 over 5? Because what's the square root of 5 times the square root of 5? Just 5? Okay, and then we can even simplify this more. Let's rewrite the square root of 5 plus, and then notice with this term here, can't those 5's cancel? So you just get the square root of 5. So this is what we get as we simplify. And then these are like terms. Let's add them up. Add up the coefficients and keep the radical the same index, same radicand, and you get 2 square root of 5. So that is the minimum value. So that's kind of interesting. No matter what real number you plug in for x here, the best one you can choose to get the minimal value is let x equal the square root of 5. And when you do that, this is the smallest outputs for y. So indeed, at x equals the square root of 5, we get the minimum value of 2 times the square root of 5, which is roughly a little under 5, I bet.
And by the way, we should know the first derivative test. I believe that is in this section. So the first derivative test says when you go from negative to positive over your critical number, that guarantees what we call a relative minimum. A relative minimum or a local minimum. And here's why that's so. Let me show you. Let me just draw this graph here. If you look at this little parabola, isn't this a relative minimum? Actually, this is an absolute minimum as well. But look at these derivatives. You know, here the slope of this tangent line is negative. So we're going from a negative, and then here the slope of this tangent line is positive. So derivatives tell you slopes of tangent lines. So when f prime goes from negative to positive, you always go left to right when you look at a graph. So through this critical number, where f prime is negative and then it's positive. So that means a relative minimum, which is right here, negative to positive means a relative minimum. If it were positive to negative, then the critical number would be a relative maximum. Let me draw that picture. Here's a relative max, or an absolute max actually. And if you look at this graph left to right, here the graph is increasing, which means a positive slope for the tangent line, which means f prime is positive. So f prime is positive, and then over here, the graph is decreasing. So we have a slope of a tangent line that's negative, which means f prime is negative.
So we remember from algebra class, downhill line gives you a negative slope, an uphill line gives you a positive slope.
And derivatives are slopes of tangent lines. So whenever f prime is positive to negative, so if it were positive to negative, that would be a relative max. But by the first derivative test, we know the square root of 5 is a relative minimum because we're going from negative to positive.
And that is all.